Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineering training with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. For anyone who enjoys space, you've come to the right place. In this episode, we talk about some of the wonders of our solar system. And I say some because there's definitely not enough time, unfortunately, to cover all of the wonders. So instead, we're covering some interesting aspects you may not know about your home system, like the timeline of our sun, the regions of our solar system, and in my opinion, the coolest part, the oceanic worlds that reside in our own neighborhoods. So I don't want to spoil any more details. So I'll go ahead and introduce our guest that so graciously came on to talk about this cool stuff. So please meet Arwen Hubbard. Arwen is a science communicator and ecologist. She earned her undergraduate degrees in resource management and agricultural ecology and her master's of science in space studies, or planetary science. Her focus was in bioregenerative life support systems for Martian exploration and colonization. Arwen lives in the desert Southwest on an off-grid homestead, helping private landowners restore their ecosystems and monitor soil health. She teaches astronomy, astrophysics, and planetary science online to all ages and enjoys nerding out about all the things space-related. So now that you've been introduced to the topic of this show and my dear friend Arwen, we are going to head into our first break. But before we do so, I wanted to take a quick second and promote our newsletter. The Monday before each episode, we will email you facts about the episode and information that wasn't covered, so bonus content. And then we will display what the following episode would be. But most importantly, send us a reply with a question that could possibly be answered by our next guest star. So if you want your questions answered and stay in tune with the podcast, head to our website under the newsletter tab and sign up today. We look forward to adding you to our community of curious people. And with that, here's our first commercial, and enjoy the show. Hi, Arwen. How are you doing?
I'm doing great. I'm excited to be here.
Yeah, well, welcome to the podcast. This is very exciting. We're going to be doing obviously some like a topic that, invokes a lot of like excitement in a lot of people, but it's not going to be a lot of surface level information like what you would think if you were to look at the title of the episode. We're going to have some surface level stuff, but then towards the end we're going to kind of focus in on something really cool that maybe not a lot of people are, I guess, aware of, which is exciting. But the first segment, this segment, is going to be on the timeline of the sun. So we're going to start where it all began, so to speak. And would you like to take it from there?
Yeah. So we're going to start with the sun because we are talking about the solar system. And everything in the solar system has to do with the sun. I mean, that's part of the name, right? Sol, that's Latin sun. And when we look at the formation of everything we're going to be talking about later about asteroids and comets and planets and all of those things, those are the leftover bits from the formation of the sun. That's kind of the afterthought of the whole thing. But there's a lot going on there, right? When we're little and we're in first grade and we're memorizing the names of the planets, it makes it seem like the solar system is this really orderly, neat place, and everything just works like clockwork, and it's sterile. But that's not what we're seeing in the science today.
Not at
The
all.
solar system is a messy, disorganized, organic, really, place made from these natural processes, and it's busy.
Very busy.
So let's go back to the sun, because that really is, for the solar system, that's our starting place. But
Right.
not really, because to talk about the sun, you've got to talk about, okay, where's the sun? How'd we get this star? Let's start
Right.
with that. The sun is a star, and it's the star we know the most about because it's right there. It's 150 million kilometers, 93 million miles, right there. You can't avoid that the sun is there.
Right.
But it's part of this larger cycle. And we've been putting this picture together for hundreds of years now. Right? It was really at the Copernican revolution about 400 years ago that we went, oh, wait a second. The sun, it's not going around the Earth, and it's one of those things, those fixed stars. It's one of those, right?
Mhm.
So I'm going to explain what our current understanding is, knowing that every day we're getting new information and new understanding. And this story in 10, 20 years, we're going to have refined it, and we're going to have differences and things that we look back on and go, ooh, well, it makes sense that we thought that, but we were wrong.
That's a great way to start this off. I'm glad that you started there. Not a lot of guests do that, and I really appreciate that because a lot of people don't realize that science changes like every day, let alone, like you said, 10, 20 years from now. So,
Yeah.
sorry, take it
Well,
away.
and that's one of the things that's so exciting about it, right? I mean, there's
Yes.
no science that's done,
Yeah.
right? We don't ever know everything. There's just more to know. And when we think that we know everything, something comes along and just flips the whole table, and we go, oops, let's start again. So it's just very exciting to be involved in, and even just to be learning about, right? There's something new to be learning all the time. So, but
Absolutely.
let's actually start. Let's start way back, as far back as we know how to start. So let's go back about 14 billion years. Now, if there was a before that or not, we don't know if the universe is part of this big cycle or not, but we have data that can start to put together this picture of the evolution of the universe. And so, these early times, that's something that the James Webb Telescope is going to help us start to flesh out a little bit.
Mhm.
But we start with a universe that has a lot of hydrogen. And that's about it in terms of the ordinary matter that we interact with. And we've got to get to a point where we can have a solar system, right, that has iron and carbon and all of these things. And we think the thing that makes that drives that, is stars.
Mhm.
So the way a star works, to our understanding, is you've got gravity, right? And gravity starts to pull things together. It pulls anything with mass, two objects with mass, it's going to pull them together. And the closer those things get, the denser it becomes, the greater and greater that gravity is going to become. So end up pretty quickly building these huge balls of hydrogen. These would have been our earliest stars. Well, eventually, you're going to get so much heat and pressure at the core of that huge ball, at this point we're going to call it a protostar, that the hydrogen atoms are going to get close enough. Now, they don't want to go close to each other because they're both positively charged, right? And you've probably played with a magnet. You can't, there's two charges
Yeah.
with electromagnetism. You're not going to get them to go very close. But if you do, if you can overcome that, then the strong force takes over and we get fusion. Now, there's a lot of steps to this process, but it's going to release extra energy, holding the star back. But eventually, all that hydrogen is going to get converted into helium, right? And then the star is going to start fusing that helium, and it's going to keep going. And it can get all the way up. These massive stars, our sun is a little bit of a different story, but these massive stars can get all the way up to where they start fusing iron. Now, the problem with when you get to fusing iron is that that's no longer releasing energy. So it collapses it, the star collapses in on itself
Yeah.
and explodes outwards. That's what a supernova is, right? It's type 2 supernova. So now we have a huge mess of all of this material that gets blasted out into space. Most of it's still going to be hydrogen because those outer layers, they were never at the core where the fusion was taking place. But now we have a bunch of what we call metals. Now, in the space sciences, the term metal is used differently than how the chemists use it. So, to a chemist, a metal is this whole, it's got to be good at conducting. It's got to be, what are all of the different things that it has to be? Usually solid at a room temperature, blah, blah. Okay.
Yeah.
And for an astronomer, a metal is anything that isn't hydrogen or helium.
Right.
So the rest of the table, right? That's a metal. So we've got all these metals out there. Now the process happens again and
Mhm.
again and again. And the more massive the star is, the hotter it gets at its course, the faster it goes through that process. So this process probably happened about 4 or 5 times before we get to the nebula that collapsed to form the sun.
Oh, that's interesting. I didn't know it was 4 to 5 times. I was always told it was 2 to 3. Wow.
So yeah, it's probably just looking at the way that we estimate that is we look at the percentage of these metals in the
Mm,
sun, and then
mhm,
we make different mathematical models and say, okay, which one fits it, right?
mhm.
So we see that the sun has a lot of metals. It's a high metal star. And this probably happened about this collapse into the sun about 4.6 billion years ago. And there's a lot of debate right now about how big of a group we formed with, because one nebula does not equal one star. Usually,
Mhm.
one nebula is going to equal hundreds of stars, but sometimes it might equal just a few stars, right? It just sort of clumps up, and each of those becomes its own stellar system or its own solar system. Now, I say system because we
Mhm.
think that most stars actually have planets, that the vast majority of them do. And it wasn't until the 90s and then really into this century that we were able to start detecting them.
Right.
So that's one of those things we're not really sure right now what, how many other stars. And if we did form with stars, we've had a lot of time to drift apart as we are orbiting around in the galaxy.
Right.
Because just as Earth is orbiting the sun is orbiting in the galaxy.
Right.
And we're orbiting a supermassive black hole, which just recently an image of it was released. So if you haven't checked out the image for Sagittarius A star, it's really amazing. It's definitely worth checking out.
I was a little bummed. It's smaller than I would have hoped, but still really
Yeah,
cool.
yeah, it's a lot. There's now that's another topic. So you
Yeah,
get into
yeah, yeah.
the image for Sagittarius A star was so much harder than M87 star. But there's really is a size difference
Oh
between the
yeah,
two, right?
for sure.
M87 star is like 6 billion times the mass of the sun,
Yeah.
where Sagittarius A star is 4 million, right? And
Yeah.
we say only, that's still pretty big. But anyways, coming back to the story of us, because this
Yeah.
really is the story of us. I mean, this is how our bodies, this is the material that makes our bodies, right?
Mhm.
Um, Something has to trip the balance in that nebula, right? That nebula is just out there, and gravity is kind of collapsing in, but there's a little bit of it's got some thermal pressure pushing back out. So some sort of event needs to happen. Could
Yeah.
be the shockwave from a supernova, or one of the leading ideas for our system is that there was probably a neutron star collision nearby that
Oh,
went off, and that may have triggered the collapse for our system to start forming.
cool.
So we get this material collapsing in. And at the core, we get this big ball, which is the young sun, the proto sun.
Mhm.
But swirling around it, we end up with what we call the protoplanetary disk. And this isn't very much mass. It's
No.
it's
What
what the planets are made from. Yeah.
isn't the sun like 99.8% of the mass of our solar system?
That's right.
Yeah.
That's so, and then that other like point two, almost
Yeah.
all of that is Jupiter, right?
Yeah. Yeah.
And then we're just like we're tiny. I don't even know what the mass for the Earth is, but we're minuscule. Um,
Yeah. Yeah.
so we get the sun though, and the sun, it's going to go through the same process that we see with other stars. Um, but we'll come back to what's happening with this protoplanetary disk. But let's start to move into the future a little bit. So
Mhm.
the sun, it is a protostar. It gets enough heat and pressure at that core. And this is somewhere in the realm of 10 to 15 million Kelvin.
Yeah.
So on this scale, you can think of Kelvin basically as the same as Celsius, right? They're only off by, you know,
Mhm.
270 or something like that. So it once that fusion starts, it becomes what we think of as an adult star or a main sequence star, which is what the sun is right now.
Mhm.
And since it's a low mass star, our star is actually a dwarf star.
Yeah.
It's predicted to live much longer than those early than our grandparent stars, right? Those had fast lives, maybe only tens of millions of years, which is really, really fast for a star. But the sun, we think, will spend about 10 billion years or so. on the main sequence or as an adult star.
Mhm.
But over time, it's going to end up running out of hydrogen to fuse into helium at the core.
Yeah.
Now, there's still going to be tons of hydrogen out on the outer layers, but at the core, we have this buildup of helium ash. Now, it's funny to think about helium as being the dense, heavy material that sinks to the bottom, but when you compare it to the hydrogen, right, that's what it is. And this is in a plasma state too. So the hydrogen, we're just talking about a proton. That's it.
Yep.
So we're going to get this buildup over time of more and more and more helium.
Right.
Now, helium takes much higher temperatures to fuse at. So it's not going to fuse until it gets to about 100 million Kelvin. So we don't think there's much helium fusion happening. But to get those temperatures, you need more pressure. So the star is going through this process where the hotter it gets, it's going to push out against that gravity, right?
Mhm.
And then there's going to be less weight crushing in. So when the hydrogen fusion slows down, the star is going to contract a little bit. It's going to squeeze in. And as it squeezes in, the temperature starts to drive up. When you get to high enough temperatures, then it can start fusing that helium. And at that point, the sun is going to switch into a different stage in its life, which is its red giant stage.
Yeah.
This is probably bad news for Earth because that means the sun is going to start swelling and getting bigger and bigger and bigger and bigger.
Mhm.
And it may come out as far as Earth's orbit. However, orbits are not stable. The planets in the solar system have moved around a lot. We don't know if Earth's going to still be there. But another discussion, Earth will be a very, very different place if at that point. And if our descendants are around, they're not going to be humans anymore. They'll be way different than us.
I'd be impressed if we were.
Yeah, species don't stay the same for very long, for more than a few million years, typically. So we won't see. They'll see. So
whatever's here.
Yeah, if they're here. But the sun then enters into this red giant stage. And this stage doesn't last for very long. And then it starts to fuse that hydrogen and it goes to carbon. Now, we'll get a little bit of oxygen in there as well, but really just carbon. Our sun doesn't have enough mass to get to the higher temperatures to keep going down that table to get all the way to iron. So that's where the sun will stop. And the next stage is that it pushes off the outer layers. Remember those layers that we said were mostly hydrogen? Those get pushed off and they form what we call a planetary nebula, which is another example of astronomers being really bad at naming things because it doesn't have anything to do with planets. I mean, the reason is that when astronomers were first seeing it through their telescopes, they kind of looked kind of fuzzy and looked a little bit like Uranus had looked like and reminded them of it. But really, they're not the same, right? It's the outer layers of a low mass star. And what gets left behind is the carbon. So the carbon, it is squished by all that gravity. It's crushed in to basically the densest that atomic matter can get. The atoms, the spaces between the atoms are just crushed away. And so you end up with something that was the size of the sun compressed into something about the size of Earth. And these objects are really hot, right? Because remember, the heat doesn't just disappear, right? You don't create or destroy that. It goes somewhere. So we end up with these really, really hot, really, really bright, but tiny, dense objects, which are white dwarfs. And we can see them all over the galaxy. There's a lot really, really close to us. None of them are visible with the naked eye. You've got to use a telescope for them just because they aren't luminous enough. And trillions of years, that will fade. That heat will equalize with its surrounding, and we'll call it a black dwarf. But the universe isn't old enough for that to have happened. Okay, Sam?
Right. Yeah. It's kind of funny you were talking about how the different types of the naming systems of the nebulas is off, right? I think it's off by like an order of magnitude of naming, right? The solar nebula should have been like a system nebula, and then the planetary nebula should have been the solar nebula. But
Right. I see
whatever.
what you're saying. Yeah. Well, so this is one of the challenges is that kind of going back to what we were talking about at the beginning, our understanding changes over time,
Yeah.
right? And we get stuck with these names. Now, slowly, those names sometimes do start to change. Like a favorite example of mine is we're all used to the speed of light, right? Well, when you say the speed of light, you could be meaning two things. You could be talking about the universal constant, right? Or you could
Yeah.
be talking about the speed that light is actually going, which in a vacuum is going to be the speed of light.
Yeah.
So recently, a term has been shifting. Lots of people have been using the term speed of causality, right? And so that's slowly starting to change, but it often takes effort to make it change. And then sometimes it's just too hard and it's just too confusing and it just doesn't happen. We just get stuck with these old names. And it kind of becomes like this mystery, like initiation, like, ooh, you know what a planetary nebula is. Welcome to the club. So also
That's
white,
awesome.
so neutron stars, not stars. Both you and I have been talking about recently about black holes, not
Yeah.
holes. I mean, on and on and on we can go. So yeah.
Yeah, no, it makes sense. I don't know if you know, I mean, I'm sure you know this, but it was kind of glanced over. Just talking about how dense the inner core is of the sun. So a lot of people think that like the light that you get or the energy that you get off of the sun is like instantaneous. What's not actually to escape the inner core takes about 200,000 years.
Right.
So yeah, because
Yeah.
everything has to travel, a
Wait.
nanometer, like nanometers in size to hit the next atom, to hit the next
Mhm.
atom, to hit the next atom. And so it takes a really long time and everything's super, super delayed. So
Right.
it's not instantaneous. It's really
It's
cool.
not. Yeah.
Yeah.
And
And
that's actually very similar to jumping back to the cosmology bit. But people have heard about the so-called dark ages, right?
yeah.
That time period in the early period of the universe where the universe was still expanding. We talk about it being very opaque.
Mm,
There was light, it just was bouncing around the way we're talking about at the center of the sun. And it
yeah.
wasn't until the universe got a little bit more transparent,
Yeah.
right, that it was able to escape. And that's what that light that we see, that's what the microwave background radiation is. So,
Yes.
yeah.
And that's a beautiful picture.
Oh, it
So
is. Yeah.
So the only other thing that I think we should probably touch on before we head into our first commercial is I don't know, like we did explain like what solar system is, right? I mean, it's kind of, you know,
Ooh,
just
mhm.
subject to what we call our star, which is Sol.
Yeah.
Nobody really knows the name of our star, which is actually Sol. So it's
Yeah.
yeah. So solar system to pertain to Sol.
Right.
So yeah, and it's
And
its system.
yeah, and thank you for bringing that up because there's actually two different ways to think about what the solar system is. Because you could think about what is within the sun's gravitational influence, right?
Mhm.
And that's going to go all the way out to the Oort cloud.
Yeah,
But then there's also the sun's electromagnetic influence.
yeah.
So when you hear someone say the Voyager missions have left the solar system, what they're talking about is they've left the electromagnetic solar
Ah,
system, right?
okay.
But they have not gotten past the Oort cloud. They won't do that for thousands of years. I would run the number on it, but
Right,
that's really far. I mean, that goes out a light year,
right.
probably. That's another
Yeah.
one of those things we talk about in science, like as if we know for sure.
Mhm.
We don't know for sure.
Yeah,
We don't have we don't
right.
have all of those examples, but we think it should be there. It matches all the rest of our models. Like it makes a lot of sense.
Mhm.
And we'd bet billions and billions of dollars that it's there, but maybe not. Right.
Yeah,
So
and that electromagnetic influence is called the heliosphere.
that's right. Yeah.
Yes. Yeah.
So helio being the Greek word
Mhm.
for sun, right? So we use sol and helio. Yeah.
Beautiful. Chef's kiss on the first segment. So we're going to head into our first commercial break. And then when we come back, we're going to be talking about the regions of the solar system. So stick around. Well, we're back. This is segment 2, and we're going to be talking about the regions of the solar system. And I'm really excited for the first portion of this segment because of the conversation we just had off the air. So I'm going to introduce it, and then Arwen's going to blow yours and my mind for a second time. So when we look at the solar system, we think of the many bodies that inhabit it, right? We think of the 8 planets, the many dwarf planets that we have, the over 200 moons that have been identified, and then the millions and millions of asteroids and comets. So would you like to take it from there, Arwen, and talk about the pop culture versus the planetary science perspective of what I'm trying to say?
Sure. Yeah. Well, this is one of the things that we see happen in, I think, any field in science, is that there is a lag between when the scientists come up with an understanding and their perspective changes, and when that gets to the public. And it would be fascinating to talk with folks from other fields and see to what degree this is for their fields. But in planetary science, we see this really interesting divide between what we as planetary scientists think of and understand planets to be and what the public sees it as. So we actually got to step back for a moment. And we do a lot of stepping back, but don't worry, we're not going 14 billion years. We're just going to go 400. So if we go back, and let's go back to Copernicus, right, and Galileo, Kepler, right. These are the characters that we're going to be thinking about. The understanding in Western science at the time had a geocentric model, and this model was heavily influenced by the church and this idea that God's creation was perfect, Earth was at the center, and everything went around Earth. We had basically 2 different classes of bodies, right? There were the fixed stars and there were the moving stars, the planets, which included the sun and the moon, and then the visible planets that we think of today. But then math and observations throws a wrench in all of this, and we start realizing, okay, no, this isn't the case. So Earth is going around the sun, right? And it takes some more observations and a bunch of time. We figure out the sun is actually one of those stars and all of that. We have the introduction of the telescope, and Galileo does something that was incredible. He looks at Jupiter and he sees that there are planets orbiting around Jupiter, right? These are what we now know as the Galilean moons. Right. And, he writes about these planets, and then we start finding more, right, around Saturn and on and on. And it takes a while for this idea to get to the public, right? And it really isn't until the 17 and actually 1800s that the public starts accepting this idea that, okay, we have this heliocentric model. But along with that, when they're taking this in, they're bringing the assumptions that they had in this heliocentric model. And this is that the heavens are perfect and that they're created, this very strong, like, let's not challenge the church and the church's authority, and God put them in these perfect little orders to communicate to people, right? Now, planetary scientists don't really exist yet. The field hasn't split. Planetary science really starts in the 1960s with planetary missions. So it's all astronomers at this point. Today, we think of ourselves, planetary scientists, we think of ourselves as a separate field. Astronomers think of us as a subset of their field. That's just one of those kind of fun little politics there. But the public isn't getting their information about the solar system and about space from astronomers. They're getting it from astrologers. So the astrologers, what they're doing is they're making big bucks by selling almanacs, right? So every year they're printing new ones and they're making a fortune, right? They used to work for like the rich families, but then that kind of fell out of favor. Now they're selling to the mass public and they're doing way better. But they have to figure out a system in which they can make it simple enough for them to be able to sell this every year. So at this
Hmm.
point, we've discovered basically anything that is not a fixed star is getting called a planet. At this point, we're not distinguishing between asteroids or asteroids, comets. Well, comets we do if they come close, but asteroids and planets and things like that. So they limit down the planets to the primary body. So they start excluding the moons, which in planetary science, we don't exclude the moons. They have the same way, they have differentiation. So in planetary science, round moons like the moon, like Io, Callisto, those are planets, right? We never stopped talking about those as planets. Kicking them out of being planets was what the astrologers did to sell books. Then they started kicking out all these other objects. So we end up with these, very small list of memorizable planets.
Okay.
And this is what really shapes the public's opinion on what planets are. We can get into the 20th century and like lots of interesting debate about when we do finally get telescopes that are powerful enough, we can start to distinguish between asteroids and planets. But in planetary science, we have always and continue to consider rounded bodies that are not stars. That's basically what we think of it, okay? So it's massive enough that gravity makes it a sphere, which gives it all of these really interesting dynamics that happen on the inside. We get this huge diversity of the different mineral species and chemical processes. So very different than what's happening in your little chunk of a few meter rock floating around, right?
It's stratification kind of,
Yeah,
based on density or densification,
exactly. And many of these bodies, we end up getting volcanism. We get all these
Right.
different kinds of tectonics. And so that's what a planet is to us. Now, some of you, actually probably most of you listening, are going, wait a second, but wasn't there that definition that defines planets that say it has to be in orbit around the sun? Now, you might be going, no, orbit around a star. Read the actual definition. The IAU's definition says it has to be around the sun, it has to be rounded by gravity. Everybody's fine with that, right? Since the 1950s, we've all agreed on that one. And then it has to have cleared its orbit. That was manufactured specifically to fit the public's perception of a planet. The public's perception of a planet is based on those astrological ideas, not what's happening in astronomy. Now, there are a small group of dynamicists who are like really into the like clearing the orbit thing. But most of us think that that's interesting, right? That's something that maybe we could make a subcategory about, but that doesn't define what an actual planet is, right? In the same way that it would be interesting to a biologist whether the mammal was marine or terrestrial, but we're not going to kick whales out of like the mammal club because they're in the water. So we're not worried about where things are to define what it is.
That's a great reference.
Yeah. So this means that in our system, from the perspective of planetary science, we think that there's hundreds of planets. Now, not every moon is a planet. Phobos, Deimos around Mars, not planets. Those are space potatoes, right? They're not rounded objects. So that's the first thing to start out with. And we could get into other things about whether the IAU should have been making that definition and whether it's just a matter of bureaucracy or science. I can argue why it's a bad definition and why it's bad science, right? It was done in secret. It broke their own bylaws. It didn't take into account any of the history we just talked about. It didn't actually include very many planetary scientists because very few are members of the IAU. It was a split vote, yada, yada. So
I have this comes to my mind. I don't know why they didn't just say like major planets and then like dwarf planets. That way you can still kind of include all of the moons and then you can have size differentiation. That way, like, how you and I talked about, or what you brought up was that then still kids in school won't have a hard time memorizing 100 planets. They can memorize 8, you know what I'm saying?
Well, yeah. So there's a few things. They did try and backpedal and then like make the definition of a dwarf planet, which already existed. We've been using it in the literature for like decades, right? But so the purpose of the IAU is it was formed to basically have everybody be on the same page when we talk about the names of objects. So I discovered this asteroid, but somebody else in Russia sees that asteroid, and somebody in Chile sees that asteroid. We can have a common name to talk about it, right?
Yeah.
And so no round objects had been found since Pluto, right? 1930, that was really the last planet that we had found. And then fast forward to 2003, and we start finding a whole bunch. So like Brown's team starts finding a whole bunch of these dwarf planets. And so they had this bureaucracy challenge of going, what are we going to name it? Because planets are traditionally, like planets are named after Roman and Greek gods. And so they rushed this process to figure out, what are we going to call it? So still, that definition really only is, how do we name these objects? But it has been taken as, what are these objects? So first of all, there's that confusion there. But then the problem is they're talking about a top level category, right? We can still talk about, is a planet a primary or secondary, right? Is it a primary or a satellite? Is it a terrestrial or a gas giant? Is it, getting into all of these? And years back, actually, there was another definition that was proposed, I think Stern et al., that said like Uber and Unter planets, right? Which basically was, does it have gravitational dominance or not? But that really just depends on where the object is at the time. You stick Earth out in the Kuiper Belt or the Oort cloud, we're not going to clear our orbit either. But I think all of us would agree that we're still a planet, right?
Yeah.
So, I mean, this also gets into, how does science work? Is science a top-down authoritarian process, or is it a bottoms-up democratic process in which things evolve in tandem with the use and the understanding?
Yeah.
So you will still hear people in this very kind of snide way be like, Pluto's not a planet. They can say it as many times as they want, but go to the literature. And since 2006, there's been thousands of planetary science papers published, and planetary scientists continue to use the term planet the way that we have since Galileo discovered Io and Europa. Like, it's one of those things. So, but that to me is exciting. Now, the thing about kids having to memorize the planets, why are we making kids memorize the names of planets? Why don't we talk to them about the different types of planets?
Yeah,
the different categories of planets, right? In undergrad, I had a crazy teacher who made us memorize the entire periodic table of elements. But most of the time, you don't. I forgot it after the exam. Most of the time, you don't have to, right? You just know, you're like, oh, okay, there's the alkali metals, and there's that's
it's the
it.
How,
that's fine.
How you reference it exactly, how it's structured exactly.
We don't memorize all 5,000 and some mammals, but we do know that there are rodents and primates and that sort of thing. So the whole save the kids thing it's just a weird argument. It's like, do you want them to learn, or do you want them just to memorize these weird facts? Now, I love the planets. You might have gotten that idea about me, and I love to talk about like everything about them. But that's not necessary, right?
Agreed.
So why don't we, any other thoughts on this before we kind of transition into these different zones?
No, you hit the nail on the head, and I just had that last thing to throw on. So I think we're good. Yeah, let's transition to, I guess, the zones.
So the zones are populated by different kinds of objects. And actually, when we get back to the formation, so I promised we were going to go back to that protoplanetary disk, right? So our understanding of how planets form is that they form from that material that was left over from the sun. And it's spread out like a disk, just because, think about spinning pizza dough on your finger, right?
Right.
It's going to spread out. Same thing there. Now, we think of space as being really cold. But if you're next to a star, it's not cold, right? The closer you are to a star, the hotter it's going to be. And the farther away, the colder it's going to be. And then you're going to have that gravity well. So you're actually going to have, even though it was all the same material, you're going to have a gradient, right? Where you have certain materials in one area and other materials in the other area. So the main force that's going to be working, though, is the temperature. And we know that different materials freeze at different temperatures.
Yes.
So planets that form, and not just planets, but also asteroids. Asteroids are basically the little pieces that never made it into a rocky planet. And comets are the icy chunks. They're going to start to be able to clump together and accrete in higher temperatures. And so that's why Earth is made from a bunch of iron and nickel, but we're not made from very much hydrogen or helium. Now we've got hydrogen in the water, right? Water is actually really, really abundant.
Yeah.
We'll talk about that next segment. But we're this dry, rocky planet, and we're really little because there wasn't very much of that big stuff for us to form from. Now, as we start moving farther out and we cross what's called the frost line, sometimes you hear it called the snow line or the ice line, basically the distance away from the star where water can be solid, it's stable and solid, right? Water can be solid inside the frost line where we are, but it's not going to stay stable, right? So outside of the frost line, ice is a mineral anyways, but we can think of it more like a mineral when it's out there. And so these other bodies, the big ones, they would have been able to grow faster. Now, there's actually some debate on the formation of the gas giants, whether they formed from collapse or this sort of bottoms up accretion process that we've been talking about. And that's an area of more debate. It's one of those things that gets presented in textbooks as if it's settled, done, no argument. But no, this is something that we're still trying to figure out.
Right.
So those are the big ones that we think about. But then there's all of these little other objects. And around the big planets, they had their own little disks. So just the way the sun had a disk of material around it when it was forming, then we have Jupiter and Saturn and Uranus and Neptune as well, most likely. And so that's where we think some of their moons accreted from. So the Galilean moons or Titan, we're talking about objects which are bigger than the moon. In fact, some of them bigger than Mercury. They would have accreted around this. So our system is a little bit weird compared to other ones that we look at. In other systems, we see that there's a lot more movement that has taken place with some of these giant planets. And those big planets like Jupiter, from our observations. Now, this might just be detection bias, right? Maybe just because we're really good at finding these planets, we found a lot of them that have moved into the inner solar system. But in our inner solar system, we don't have any big objects. So we have two different zones, right? We've got our Volcanoid zone, which is basically anything closer to the sun than Mercury. And then we have the terrestrial zone. And this is the inner solar system that we're used to. It's tiny. It is really, really tiny. When we measure distance in the solar system, we use what's called an astronomical unit, AU. And that's Earth's distance from the sun. It's the average distance. So for those of us in the States, that's 93 million miles. For everybody else in the world, that's 150 million kilometers. So that we use that because it's just too many zeros to think about, right? So the inner solar system is about 2.5 AU. We get to the asteroid belt, which we think of as like this dividing zone. And that's home to Ceres, by the way, which is just this amazing planet. It was the first dwarf planet discovered back in 1801. And it's kind of, had identity crisis about what we're calling it or not calling it. But now we know that it's this frozen ocean world, just this amazing body. But we move out into the Jovian zone, which used to be called the outer solar system. But then we discovered Pluto and we discovered the Kuiper belt and the Oort cloud. And we realized that it really should be part of the inner system as well. But we call it the middle system. It goes out to about 30 AU and we call it the Jovian zone. This is also a zone where we have the centaurs. There's a whole bunch of stuff going on here. It's probably the region that the dwarf planets originally formed in. But early on in the solar system, we think that the giant planets did some migration. They did some moving around. There's several different models on this. And that's probably why we even exist, right? We think that going back to Earth's formation, Earth used to be two different planets. We had Proto-Earth and Theia that smashed together.
Oh, that's a good point. Yeah, because in most systems, typically like a Jupiter-like planet is usually closer to the sun.
Right.
And that's where we think that there was movement from the what is now the Jovian system.
Right.
Yeah, it's
Yeah.
the
And
Jovian
so,
portion of the system. Sorry.
right, the Jovian zone. Jovian means Jupiter-like, by the way. So
Ah, look at that.
um, Jove is Zeus or Jupiter. So
Okay.
yeah, so we think, and this idea is called the grand tack, where we think Jupiter moved in, Saturn came along as well. They were growing and growing, getting bigger,
Mhm.
and then the ice giants probably pulled them back out. And
Ah.
this probably rearranged our solar system, and most likely flung the little planets out, probably
Mm.
hundreds of them. This is most likely what ended up forming the Oort cloud and a debated region called the scattered disk. Some
Oh,
people think that it's an actual region. Some people think it's just part of the Kuiper belt.
okay.
But if we go beyond Neptune, we enter into what we actually think of as the outer system. And so that goes from the Kuiper belts from about 30 to 60 AU. And we have this big, big gap, which sometimes gets called the Kuiper Cliff or the Sednoid zone, because the dwarf planet Sedna is in this area. We have a big gap of thousands of AU, and then probably there's a region that surrounds us like a sphere called the Oort cloud, which is populated by icy bodies, mostly with comets and presumably other dwarf planets. But detecting these objects is really hard because these
Yeah.
objects are very small. They're in irregular orbits. The ones that we have found have mostly been on the main plane of the solar system. So we kind of know where to look for them. But
Yeah.
if you're trying to find an object which is, only a few hundred kilometers across, that is literally a light year away,
Yeah.
it's a really tricky proposition. But that's going to be the most populated area, and we have barely even begun to explore it. We visited 2 objects in the Kuiper belt. It's all been the New Horizons mission.
Right.
And maybe, fingers crossed, there might be a third target, but there's a lot of luck involved with finding the right one with the right amount of fuel and
Of course.
all of that. But what we see is that in each of these regions, there's so much more going on than just plop, 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 a couple of planets. And
Right.
trying to talk about the scale is just incomprehensible to our brains, just the vastness of our solar system. And then remembering that we're just this tiny little solar system in this big, big galaxy. It's one of hundreds of billion galaxies, and then, just on and on. But we know so terribly little about our own system. There's one body that we have landed on outside of the inner solar system, and that's Titan. And our probe didn't last for very long. Did some amazing, amazing photographs, some amazing work, but that's it. And we've sent a lot of missions to Mars, but not really, given how close it is, right?
Yeah.
We have some rovers on the moon. We landed on Venus and melted promptly. That's it, right? And a few comets, so that we have millions of objects to continue to discover. And as we're talking about planets, probably hundreds of them, maybe up to 400, 500 of these planets. Most of them probably quite active worlds.
Yeah.
Because if anything, of the dwarf planets that we have visited, we have found that they are spectacularly active.
Right.
Yeah.
I think we really get lost as human beings trying to imagine like where, we should, for how advanced we are right now, we should be here. We should know this. We should know that. We've solved this. We've solved that. But we're a very, very young species. Granted that, we don't take ourselves out in the foreseeable future. But
Mhm.
if you think about the dinosaurs, right? And obviously this is a hard comparison because of the intellect neural pathways versus the scale
Sure.
of their brains. But anyways, they were around from about 220 to about little over a little past 65 million years ago. That's
Mhm.
millions of years, right? Our species, Homo sapiens, about 300,000. I mean, give or take. People like to debate that.
Right.
But
I
just
mean,
the
we could
scale of
safely
magnitude.
say a hominid's 2 million years, right?
Yeah,
Yeah.
safe to say, yeah, about that. So, I mean, we're a drop in the bucket. We have a lot of growing room. There's so many things that are unsolved. There's so
We
many there
do.
The more data we get, the better.
Yeah.
That's why Arwen's saying like we there's so much that's out here and we just have no idea. But we'll get
Yeah.
there at, one data point at a time. You can only point a telescope in one region at a time. It's not like you can take a 360 pano.
Yeah.
Yeah.
And this gets into also like what do we put our resources into? There
That
are
yeah.
so many interesting, valuable topics to be studying,
And
right?
then that
Like I
ends
have
up
my
getting
baby
political.
planets that I'm like, I want to go to those planets. But like all of these other just fascinating ones that
Yeah.
it takes money. Now, space exploration is a lot cheaper than people like to make it out to be, right? It's the scapegoat for a lot of things. And when you actually look at what the budget is compared to our budget for like lots of other things, it's not that big. But
Yeah.
from the perspective of, us,
hmm
it's the like as individuals or even as like just counties or states, local governments, it's a lot of money, right? And
hmm
it's a lot of time, but there's so many people who are just passionate and want to do it,
Right.
right?
Isn't it that the NASA budget alone is like fourth? No, a fourth of a tenth of a penny or something like that?
I don't know the
Whereas
actual numbers, but it's in that like less than a
it's
percent of
so
penny,
small.
for
Uh,
each tax dollar. Yeah,
Meanwhile, the US military budget's like over $400 billion, and we spend trillions and trillions of dollars per year in US government money. But we get upset whenever, NASA's trying to put a satellite up there or a telescope.
right. Yeah. Well, and this could
Semantics.
be its own thing, but like the importance of the space program in understanding
Oof,
our own planet, right? When
oof.
we talk about planetary science is one of the absolute most important things for understanding how to take care of our planet.
Yeah.
Because in a lot of other sciences, let's talk about chemistry. You want to know what happens when you mix two chemicals? You go to the lab and you mix the two chemicals, but you can't do those experiments with the planet. I mean, we're kind of doing them on some levels, but we
Eh,
probably should be a little bit more careful. But if we want to understand um, the dynamics of atmospheres, well,
mm,
guess what? We have some sister planets that we can look at those differences and try and understand. We can't perform the experiment, but the second best is having a lot of examples to look at and compare between.
yep.
And then our fleets of satellites that are Earth observing satellites. Without those, we wouldn't know when the hurricane was coming. We wouldn't be able to track any of this stuff. It's and not to mention that it's completely essential to our entire modern way of life,
Yeah.
right? Like we're using satellites to communicate right now. You
Yeah.
can't gas up your car without like satellite communication. Like it's just so part of our world.
Oh,
Um,
absolutely.
and that's one of the reasons too. I think it's just important that people know about it. One, it's the space stuff is just cool and awesome, and isn't it amazing?
Yep.
But it's also really important to
Super
our
beneficial.
survival as a civilization. Maybe not as a species. Humans are generalists. We'll fight to survive, but
Yeah.
our civilization,
Good point.
that depends on space.
Good point.
So,
Good point. Yeah. So, do you have any thoughts before we move into our second commercial?
oh, so many. But why don't we go into the commercial? Because this next segment I'm excited for too.
Okay, sounds
So,
good. Yeah. So, whenever we come back from this one, we're going to be talking about the oceans in our solar system. Super exciting. I'm sure you're curious. So, stick around and find out. Well, I hope you stuck around this far because this is the last segment of this episode, and we're going to be talking about something very interesting. Not something you really think about outside of Earth, right? We think of Earth as being the water planet, in our solar system, but there are plenty others. So I'll hand it off to Arwen where she can explain that. Go ahead, Arwen.
yeah. So first of all, let's talk about water for a moment. Water, as we all know, is H2O, right? Two hydrogens and an oxygen.
Mhm.
Now, going back to the formation of elements that we were talking about before, when we look at the universe, we see that In terms of ordinary matter, it's mostly hydrogen. There's a lot of hydrogen. That was from after the Big Bang. Now, the second most common element is helium. But helium is really stingy. It's called a noble gas for a reason. It doesn't interact with pretty much anything. It does its own thing. The next most common is oxygen, right? Now you'd think carbon, but actually carbon is involved in a lot more fusion processes to lead to some of those heavier elements. So the two most available and abundant elements in existence are the two things that make water. Water is actually very common throughout the universe. And for life as we know it, it's absolutely essential. Now, Earth is weird because we're an EWOW, we're an external water ocean world. And we're actually the only one that we know of. Our planet is not made from ices. We're not made from water, and yet we've got some water. So there's a lot of this is another area that we're still working out. And then again, the textbooks are going to tell you it's all settled. It is not settled. But where that water comes from, there's a lot of different questions about that. And the kind of the big ones is that some of it was actually made in the earth. And when a volcano erupts, that cloud that you see, a lot of that CO2, which was building up the early atmosphere. And if you wonder about Venus's atmosphere and why it's so thick, that's probably because of those volcanoes.
Yeah.
But one of the major things in it is going to be water. So current estimates assume that about half of Earth's water, so think about all those oceans, comes from the volcanoes. But the other half, we think, come from asteroids and comets. And yes, asteroids. We have identified the specific ones we think brought water to Earth that formed outside the frost line. And then when Jupiter and Saturn were doing that moving around, they shuffled around a bunch of stuff in the solar system and flung lots of those comets and asteroids towards Earth. And we think that delivered a bunch of the water to our surface. Now, we think that probably happened to Mars too, and possibly to Venus. For a long time, the accepted idea was that Venus was a warm, wet ocean world just like us up into about 750 million years ago. Right now, there are some challenges to that have just come out that said, oh, maybe that we actually have a dry formation model. So it's kind of back up in the air about whether Venus really was a water world or not. Mars, it's really very clear that it was an external water ocean world like us. So we see that, I mean, you just look around, look at any of the photos from the rovers, which we purposefully put in dry lake beds and areas where there would have been water.
Right.
But these are very unusual oceans. There are other worlds in our system that have way more water than all of Earth combined. Let's start with Ceres. Now, Ceres today is a frozen world, but from what we think it used to be we think it used to be a planet-wide briny ocean. So the layers underneath are frozen mud. Now, Ceres is very little body, and it doesn't have any tidal interactions like the planets we're going to talk about in a moment. And we don't really know why it seems to have less of our heavy radioactive metals, which are the source of a lot of internal heat for worlds like Earth or Pluto or places like that. So that's our first one. Now, it does have an ice volcano, which ice volcanoes turn out to be what we think far more common in our solar system than what we think of as normal volcanoes. So ice volcanoes are also cryovolcanoes. They're going to work the same way, but at different temperatures. So here on Earth, we're going to have these molten, basalts and, things like that, where you're going to have to get to thousands of degrees in order to get these to actually be molten. But if you have ices, now, when we say ices in the space sciences, we may be referring to water, but we're also referring to volatile things like ammonia and methane, regardless of what state it's in, whether it's a liquid or a solid or a gas. The ices are just referring to those types of compounds.
Okay.
So those, you can melt those at much, much lower temperatures. So as long as you have a difference between your magma and wherever it's going to the surface, then you can have volcanoes. So cryovolcanism turns out is just all over the place, and it's amazing, right? So Ceres has Hunamans, and it's kind of weird because there's one giant volcano on the planet, and that's it. Right? Like there's other places that we find volcanoes, like there's a lot of them, but there's just the one. Now we think that there actually probably used to be more, but they were like slump over time.
Okay.
Yeah, so it's called viscous relaxation. But let's go out to maybe the most famous ocean world, which is Europa. Now we've already talked about Europa a few times because this was one of the 4 Galilean moons, and it's the second closest of the major moons. There are some little minor satellites that Jupiter has that are not planets. They're, again, just lumps or little potato moons. But Europa is the second out from Jupiter. And it is in an orbital resonance with its sister moons. But when we look at it, you see that it's totally covered in ice. That's this beautiful blue world with these long reddish orange rusty looking cracks on it, and there's almost no craters at all. So this is a body about the size of the moon, almost zero. There are a few, but if there's no craters, that tells us it is an extremely young surface. It's remaking itself.
Yeah.
So we think that underneath the surface, go down, and estimates really vary, but 5-10 kilometers thick ice layer, there is a planet-wide ocean with more water than all of Earth combined. So we think that this is a liquid water ocean, and we can tell this based on magnetic readings and gravitational readings because we have several have had several satellites in the area taking those measurements. So this world is probably staying liquid because of the tidal interactions that it has with Jupiter and with its sister moons. So Jupiter is 5 AU out. It is totally frozen and freezing out there in space. It's not getting anything from the sun, right? I mean, tiny bit, right? So that, I mean, it's 5, so that's, it's getting a 25th of the light that Earth is, right? So those oceans are not melted by the sun. But since its orbit isn't perfectly circular, sometimes it's a little bit closer to Jupiter, and sometimes it's a little bit farther away. So that is basically, it's friction. It's creating this friction, and there may be some radioactive decay as well. And then it's the sister moons are pulling on it as well. So you're just getting this squishing and pulling, squishing and pulling. So we suspect that at the bottom of these oceans, there are probably hydrothermal vents. And this is very similar. This gets astrobiologists really excited because here on Earth, we have whole ecosystems that thrive on our hydrothermal vents, completely separate from our terrestrial photosynthesis ecosystems and food webs up here. They're doing their own thing. So I think that this environment is very similar to what we have on Earth.
Not even just around the hydrothermal vents, but also subsurface, like biology as well.
Right. Yeah. Chemosynthesis is all over the place. There's this whole domain of organisms called archaea, right? Like a huge branch. And many of them are what we think of as extremophiles. They live in these environments that to us would be very, very extreme. Just high temperatures, really acidic environments, all sorts of stuff. So this is kind of the world that we point to as our ocean world. And it actually has a mission going back. NASA's next flagship mission is the Europa Clipper. I think it's supposed to launch in 2027. And the journey is a several-year journey. Have to look at how long that's going to take, but we're in like the 4 or 5 year range. And it's an orbiter around Europa. So So one of the
Oh,
things it's going to be studying it, and one of the things that it will be looking for is potential landing sites. So we could send a mission back and maybe go and look.
cool.
Now, this is the most famous. There's also Enceladus, this little world that basically looks like a snowball around Saturn. And so this planet, this is tiny. This is like, I don't know, it's like the size of Egypt, right? But still fits all of our criteria to be a planet. And this one, there's debate on whether it's a full subsurface ocean or whether it's pockets of it, but it's shooting geysers of water out.
Oh, yeah.
And we actually flew Cassini, the craft, through, and were able to basically taste what was in it. And we found, obviously, water, right? And that's what's responsible for making the E ring around Saturn. We found multiple salts and organic compounds.
Nice.
We already know it has all the ingredients for life as we know it.
Cool.
These are the most famous, but there are literally dozens of other worlds that we think have this same kind of structure.
Mhm.
So we think of the terrestrial and the Jovian planets, right, as being like the main types of planets. But no, our system is actually full of these icy bodies, which often have rocky cores, right? These silicate cores, but then they have layers of water ice. And that the ice, works like a mantle. They often have these subsurface oceans and detached shells of ice on top. Now, in some of the places like Titan is a really interesting world in terms of oceans because this planet has an internal water ocean, but it has a surface methane ocean as well, which is the only place that we've seen it so far. Now, who knows?
Cool.
Maybe that's like the most common one when we start exploring exoplanets. But right now, it's the only one that we know of. But this world, this planet, it's got this huge ocean underneath. Again, more water than all of Earth.
Yeah.
With all the ingredients for life. Now, I should mention, these are called IWOWs, internal water ocean worlds. And they're really interesting on a lot of levels, not just the geology, but also the idea of civilizations and the development of life. So the fact that we're here on Earth's surface is crazy. Because living on the surface of a planet, your star is like growing all the time. It's got these flares. The most common type of star, which are red dwarfs, are really cranky stars. They're constantly sending out these huge flares. They're just radiating the surface of the planets close to them. There's asteroids. If you've got a supernova that goes off nearby, like that can wipe out your life on the planet. Your atmosphere has to be just perfect. I mean, it's mind-boggling that we're here, right? Saying that it's astronomically unlikely is an understatement. But IWOWs, they've got all the ingredients for life. They're protected from the tantrums from their stars. They're protected from major impacts like what killed the dinosaurs. They have this great system going for them. So if there are other civilizations out there, there's a pretty good chance that they would be in these IWOWs.
Yeah. There's a doubling effect, right? I was thinking about how it's capped with ice. However, the ice is, and then underneath the ices, there's the oceans. So ice is like the best thermal insulator just known in the universe. So I'm thinking of the radiative heat from the core working, in friction, expansion, contraction from these, and then pushing out the heat through these hydrothermal vents, but then also keeping the heat in and in making it more habitable as you reach out towards the I guess the ice shelf.
Yeah, towards that crust.
Right.
So cool. Yeah.
Sorry, I just wanted to say that.
No,
that was really
it's really cool. And you can think about that with unbound planets. So unbound planets, that's a type of rogue planet that was in it's just orbiting They would be unlikely to develop radio communication, though, because radio is light, right?
Yeah.
And they're not going to get light under 10 kilometers of ice. And if they aren't near a star, anyways, so they probably wouldn't develop the vision based on electromagnetism, which would make it less likely that they would run into the other kinds of electromagnetism to then use for communication. So now I'm not saying that there are civilizations on Europa or there's civilizations deep in Pluto, but there could be. We've never looked, right?
Yeah.
And if they're there, they're not using radio. That's how we would know that they're there, right? It's the electromagnetic leakage. And they also wouldn't be very incentivized to go to the surface of their planets.
Nah.
So maybe there'd be adventurers. But with us, we know there are stars out there because we
You can look
see
up.
them, right?
Yeah.
We look up, but they wouldn't necessarily have that. So it's just this really interesting idea of when thinking about aliens and things, that those would probably be way more habitable worlds. And they seem to be, as far as we can tell right now, the most common kind of planet, right?
Yeah, that's true. Everyone's looking for the Earth 2.0, where you think you're going to find life on a terrestrial planet. But why do we have to just, envelop terrestrial planets?
Yeah.
Why not these ocean worlds? These IWOWs.
These IWOWs, yeah. It makes sense why we would do that, because life is probably really, really diverse. Maybe there's lots of life that doesn't need water. It's abundant, but maybe it doesn't need water. Maybe it needs totally different temperatures. Maybe it doesn't need carbon. All those ideas about silicon-based life, things like that. But we do know that life can work the way it does on Earth.
Yeah.
We know that life can be carbon-based and use water. So it gives us a starting point. And when we're talking about exoplanets, we aren't at the point where we can image them yet.
Yeah.
Planets in our own system, we can go there. Some of them. If we're talking about, say, Make, we can't go there yet. It's just a few pixels on a screen, which is what all the planets used to be like to us. They were just pixels until we started visiting them. But now we can send spacecraft. We have to be patient. It takes a decade. It takes 2 decades to get there. But we get these pictures back and we can land. We can take samples. Now, with exoplanets, there's some things we can do. We can do some limited spectroscopy and take a look at their atmospheres. Can't really see much about their surfaces yet. We can get their density, which lets us figure out, what kind of planet it is. By the way, talking about planets, the solar system does not have all the kinds of planets that we've discovered. There are way more kinds of planets. They're just really cool. Lava worlds and ocean worlds and mini Neptunes and super Earths and hot Jupiters and on and on. And then theoretical kinds that we haven't found yet, and planets that orbit double star systems, and so many cool things.
Yeah. And
So,
I think so we were talking about earlier how people say like the way that our solar system came to be is scripted and it's beautiful. I find it different. I find it that what's really beautiful is that there's so much diversity in how a solar system could come together.
Yeah. It's messy like a forest is, right?
Yeah. Yeah.
So
good point.
there's something that, it's charming to go to this manicured lawn, but there's something about that wild forest and the squirrel that's yelling at you because you walked into their territory, and the leaves on the ground, and solar system's sort of like that.
Yeah.
So,
very cool.
And there is one more IWOW. There's a lot to talk about, but there's one that I really want to talk about because this one surprises people. And we've mentioned it before, but it's Pluto.
Okay.
Pluto is the second most active planet in our system that we know of geologically. The first being us. When we look at Pluto, its surface is covered in moving glaciers. It has towering mountains and ice volcanoes, and we can see very young, there are some areas that are old, very young surfaces, and we think that it's got these subsurface oceans, which you'd find possibly Earth-like life there if we were to go down and look. It's got atmosphere and clouds, and it changes drastically. We were in such a rush to get New Horizons to Pluto in 2015 because Pluto is close to its closest approach to the sun, right?
Yeah.
And then it's going to sweep back out, and Pluto's orbit is roughly 250 years.
And
So
it's extremely eccentric too.
yes, right. And that really, really eccentric orbit means that sometimes it's quite hot, I'm putting those in quotations, and sometimes it's very cold. So we think that the atmosphere changes drastically between those. But what it's given us a hint to is what we might expect to find in these other Kuiper Belt worlds, because a lot of people thought that Pluto was pretty much going to look like a colder version of the moon. It was going to be this dead world. And it does have its largest moon. It has a whole lunar system, but it's actually a binary planet. So Charon and Pluto,
yes,
they are really large compared to each other. We think that they actually formed in the same way that we think Earth and the moon formed, with this impact collision and throwing off this secondary body. But their barycenter is outside of the two. So the Earth, the barycenter for the orbit between, now barycenter, that's that center of mass between them that they're both orbiting around, is inside of Earth. So it really looks like the moon is orbiting around Earth, even though Earth and the moon are orbiting around the center of mass between them. With Pluto and Charon, they're going around each other. Now they're tidally locked at this point. So the internal heat, some of that is probably left over from the tidal interactions that they would have had, but most of it is probably coming from this radioactive decay that would be in the planet. And so a lot of these other ocean worlds, they probably have these this radioactive decay as well. For some reason, Ceres doesn't seem to have it. Right? Maybe there's a little bit going on, but not enough. So when we think about those unbound planets, we think about planets in other systems, or thinking about the farther out dwarf planets, Pluto's really this best model that we have. And it really interesting matches very close to Triton. Triton, not Titan. Triton is Neptune's largest moon, and it's also what we think is a captured dwarf planet. Okay. So it formed orbiting the sun as a primary, and then got a little bit too close to that other planet and got captured. It has a really eccentric orbit too, and it's a retrograde, so an opposite. And we see on it as well, we see cryovolcanism, we see this dynamic surface, or we did in 1989, the last time we were there. We haven't been back since the 80s. Wow. So hopefully that's another one of those ones. So hopefully we can get more missions going back or even going to these planets in the first place and seeing, what's going on with them. So
awesome. I actually wasn't aware of Triton. So
Triton is fun. Yeah.
Yeah. I didn't know Ceres was that cool either. I need to take a deep dive, I guess.
Ceres is awesome. Yeah. And it's one of the 3 dwarf planets we've visited by spacecraft. So including Pluto and Charon. It was in 2015, which was a great year for planetary science. So the Dawn spacecraft went to Vesta and Ceres. So we have really great imagery for both of those bodies. And Vesta is this on the edge. It's a protoplanet. Okay. So we start to see some differentiation. We start to see some of the features that we would with a planet, but it just didn't quite make it there. So it's really fascinating to actually study that when looking at the development of planets.
Definitely.
Because it's so close. Pluto's 40 AU away. When you talk about trying to visit Enceladus or the Death Star moon, that's another fun one to look up, which is Mimas around Saturn. It looks just like the Death Star.
No way.
Seriously, do not take my word for it. Look it up. It looks just like it. We knew about the moon before the movies came out, but then we got images of it afterwards, and it's a spitting image. It's got this really big complex crater. Are you looking at it right now?
Yeah.
Yeah, it's great. So another probably eye wow. Ganymede, Callisto, those are going to be eye wows. We can just keep going on and on.
I
Oh,
have
you're
to share
bringing it up
this.
right now. Okay, yeah, look at that.
It's awesome.
So, yeah.
This is cool. This is going to be a TikTok video of mine. I'm going to have to do something like this.
Now imagine if we went into the subsurface oceans and found life there. What would we have to call them?
Oh man.
Have you the
Ooh. I don't know. Oh wow. That's a good one. That's a good one for the comment section. If you have a good name for a species that we find, or just a civilization,
or the civilization, or just the life forms,
yes,
right? What would they be?
Yeah, super curious. So I just had to share that. That was cool. Totally worth it. So I don't know how much more you would like to add, but if you don't,
yeah, I can keep going. But what would you like to talk about, though? I want to be respectful of your time for sure.
Oh no,
I know
no,
we've been going for a while.
No, we're good. So how about this? Give us your final thoughts for segment 3, and then I really would like to get some maybe advice or some parting thoughts that you may have, maybe in terms of, passions versus planetary science, or even I know you have a huge presence on TikTok, so maybe advice about making TikTok videos, whatever you would like it to be. So
sure. Well, I think I want to wrap up what we've been talking about in these 3 segments with really saying that, emphasizing we are just on the edge of this incredible period of exploration. As I was saying before, planetary science was really born in the 1960s, and it's not very old.
No.
And there's so many new fields, right? There's a whole new group of planetary scientists, which are the exoplanetary scientists, who are starting to getting to study the TRAPPIST system and the this and the that. And I also want to say, though, that you don't actually have to be a working scientist to be appreciating and enjoying this. I think that it's important for everybody to be informed to a certain extent of just have scientific literacy, but you can attend a lot of conferences now because they're online. You can be reading these papers. There's a lot of science communicators out there and classes that you can take. And if you are interested in it, this is our world. We are part of this solar system. We're part of this galaxy. It doesn't belong to one group of people. We're all part of it. So I really encourage people to do some exploring, and just also keep in mind that the answers change, right? Just because you learned something one year, right? And a lot of the videos I make, people or students that I work with, they'll get upset because they're like, well, but I was taught this and this, and now you're telling me this. I'm like, yeah, it's okay. It's changed. Isn't that cool? Look at the new stuff that we've learned. Wow. How did we figure that out? Why? And just engage that curiosity. Let yourself explore.
Absolutely. Yeah, I say stay curious after almost every video, because it's super important to do so. I think our education system does a pretty good job of squashing curiosity, but we want to stay curious throughout our whole lives, because without being curious and asking questions, it gets a little bit boring. So this stuff's very fascinating, and it changes all the time. So, and yes, you don't have to be a scientist. You don't have to be, you don't have to have a 4.0 in physics to understand these things. It's just fun to talk about. It's fun to learn, fun to read about, and fun to watch. So just stay tuned.
Okay to ask questions.
Yeah.
Right.
Yeah.
Not only is it okay it's great when you don't know something. That's not a shameful thing.
Yeah.
It's an opportunity.
Absolutely. I
So
couldn't agree
yeah.
more. Do you have any thoughts about TikTok by chance? Because I know TikTok's a very interesting platform to share information. Right now, it's it's
It's a
anybody's
weird
game.
place. Yeah. Yeah, so I've been on TikTok for a while. I was kind of terrified to get on it because
I get that.
it's uh it's an intense world, and it's the platform's good. It sucks you in, right? It's really well designed. I'll be uploading a video, and then it'll take me to like the home page, and I'll start scrolling, and like I'm like, wait, I was supposed to be doing something. Here I am
Mm-hmm.
scrolling. But there's actually a lot of really interesting stuff. You can curate what you want to see, but you have to be
Yes.
really intentional about it, and like
Yeah.
periodically stop and go, okay, all right, all this political stuff is important, but goodness, it is not good for my mental health right now.
No.
I am gonna go learn about astrophysics
Yep.
or geology or whatever. There's so many really cool working scientists and science communicators. So I am there if
Hmm.
people want to check me out. So my account is space_STEM. So
Yes.
STEM, science, technology, science, technology, engineering, and math.
Yes,
So
it will be linked. Don't worry. You can
yeah.
find it on the website for this exact episode.
Oh
Just go to
yeah.
the episode page and then you'll be able to connect with Arwen and it'll take you right to her page. So, yeah.
And I recently opened Instagram with that, and I have
Ooh,
YouTube as well. Those are still starting to be developed. I think that I will be doing a lot more on YouTube because it's a little more my style. I'm not, I, I got really dynamic in this conversation, but I'm not
mhm.
that like super bubbly. Like you're not going to see me do a dance. I'm not going to do
No.
any of those memes. And they gave me like the ability to do 10-minute videos, but I don't think people are going to sit through 10-minute videos on TikTok. So I'll be
It's
doing
fair.
a little bit more of that on the YouTube.
Mhm.
And I also do have my website, and that's arwenhubbard.com. And so I do live courses and online courses. So if you want to do like a full astronomy or astrophysics course with me, I do those as well. So that's actually my main income and profession right now is teaching all of this incredible stuff and just getting to hang out and
Heck yeah.
research and answer questions and ask questions with all of you. So yeah.
That's exciting. I'm kind of in the same, I don't know, the same shoes as you. I would like to expand on YouTube. That's something that we're trying to do right now. One thing that we're trying to do is we would like to have live stream sessions where we could take donations, but the donations though will be dictated upon the crowd, right? We'll give like we'll do like a multiple choice or a poll about which ones that you would like to send, and it'll be something environmental or social for a good cause. And we would like to do that hopefully by next year. So we're trying to hit 1,000 subs so we can do so. Hoping. Be very
Yeah.
nice, but that's what we're shooting for. And yeah.
So if any of you are listening, I know that Sam is not asking this directly, but I'll ask for all of you. If you're not subscribed to Everything Steam on YouTube, you should go and subscribe. Help them get to that 1,000 because YouTube has the whole they won't let you do certain
Mhm.
things unless you get up to the 1,000 and you
Mhm.
need a certain number of view hours
Yep.
and I understand why they do it, but
Oh, I do.
when you are a small channel, it's kind of hard to get past that first hurdle. And once you get past that, things can start to pick up steam, so to say. And
Good
but
one. I
yeah,
like that.
so for your creators, if you want to see more science content, it just really always helps us out to,
Yeah.
comment and like and any engagement.
Mhm.
It's not people deciding this, it's all the algorithms. It sticks
Yeah.
it higher up so that it can get in front of more eyes, and it just makes all of
Mhm.
this more possible for us to do and share with all of you.
Even just saying like, I love this video or asking us a question. Obviously, we want you to ask questions, but like, even if you're just like, I love this video or wow, that was pretty cool. Or I
Yeah.
never thought about this or just something like that is even just really fruitful for us because it makes us want to do the content more. It makes us
Yeah.
excited to teach you something or share really cool knowledge because that's pretty much why we do it. We find this stuff really fascinating.
Yeah. And I know it sounds really cliche. You've probably heard this from a million people, but it is real, really. That comment, that,
Yeah.
I guess the shares, all of those things make
Yeah.
such a big difference. So yeah,
Unfortunately.
and it helps with morale because the internet can be a real harsh place sometimes.
Yeah.
People like to nitpick everything, and we are human. So as we
Hmm.
said, we probably made mistakes, and that's okay. That's good, right? When people point those out, but in a nice way, it makes it a really interesting conversation.
Yeah.
Right.
Yeah.
So that's always appreciated, right? Like, oh, what about this? Or I thought this, or that makes it into a discussion because science communicators like us, we aren't the authority. We don't know everything. Our job is to try and translate
Hmm.
this into make it more accessible so that we don't have that problem that I was talking about at the beginning with
Yeah.
planetary scientists and astronomers saying one thing and then the public listening to astrologers,
Yeah.
right?
Yeah.
So we can try and get that to be a more fruitful ecosystem, right?
Yeah. And my last comment is going to be if you're interested in like reading papers, like published papers, I do believe Sci-Hub's a really good place to go. I've used that
Yeah.
a few times. I mean, obviously you could just use Google Scholar, but like Sci-Hub is a really nice spot to be if you want to look for good scientifically published papers, published and peer reviewed.
That's
Peer
important, right?
reviewed.
Yeah,
Yes.
and that could be a whole episode talking about
Oof,
the benefits and the drawbacks of peer reviewed, but that's really important, right?
absolutely.
And also,
Mm.
your public library often has subscriptions to these online catalogs, and you can just go through and read all this stuff. I mean, so much of it is going to be available not behind paywalls, but the stuff that is behind paywalls, it's a good chance that your public library is going to
Yeah.
have access to it.
Public
So,
libraries have so many benefits that people don't take advantage of. Like
yeah.
just lots of subscriptions, even like TV subscriptions and stuff, or
Oh,
streaming subscriptions.
I found out last week mine lends tools. Like you
Oh,
can borrow like tools to do stuff. Like this is so cool. I don't have to go and
wow.
spend a whole bunch of money for it because none of my neighbors have it. I don't have to go like drive an hour to like Home Depot or Lowe's or something. So yeah. So check
That's
out
awesome.
really, and the more we support our public libraries, as long as we're on soapboxes right now,
Yeah.
support your public libraries and your science communicators and the type of content, the stuff you want to see, the more you engage with it, right? The stuff you value,
Yeah.
whatever it is, the
Mhm.
more you engage with it, the the more steam it picks up, the stronger it's going to be. So
Absolutely.
yeah.
So, Arwen, is there anything else you'd like to say? If not, we can get out of here.
I had a blast. So
Me
thank you for
too.
inviting me on the show. This has been a lot of fun.
Absolutely.
And if anybody has questions about what we've talked about, I'm really happy to talk with you about it and give you more
Mhm.
information, answer questions, all that sort of stuff. So,
For sure. Or hit me up and I'll send you right to Arwen.
yep.
Yeah, for sure. Well, this was great. I really appreciated you coming on the show, and we're definitely gonna have you back for something else.
Sounds good. Yeah. So, more to
Awesome.
talk about. Right.
Awesome. Well, have a great rest of your night. This was awesome, and we'll be in touch. That is all for this episode of Everything STEAM. Now I'd like to give a big shout out to Arwen for sharing her knowledge and vast expertise. I highly recommend that you follow Arwen at space_STEM on TikTok and Instagram. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Mike Gabriel, marketed by Courtney Page, QC'd by Panipit Urixit, and the episode art was manifested by Gabrielle Edmiston. Again, I encourage you to sign up for our bi-weekly newsletter. The Monday before each episode, you get a preview of that episode and a sneak peek of what the next episode will be. And as a bonus, we'll include some information we missed during the discussion. But most importantly, reply to our newsletter with a question for the upcoming show. We will take 1 or 2 questions from the audience and answer them during the recording. And if you like YouTube, or if you know someone who likes YouTube, our goal is to get 1K subscribers by the end of this year so we can do live streams to where we can put donations towards a charitable cause. So we would like to do that and have guests on the live streams and do something more collaborative and create more of a community. So be sure to help us out and get your friends, get your family, get anyone you can to subscribe to our YouTube channel, and it's Everything STEAM. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and just fun STEAM content. Just search Everything STEAM on Instagram, TikTok, Facebook, and Reddit to join in on the fun. Once again, thank you for listening to Everything STEAM. I am your host, Sam Stanford, and as always, stay curious.